Hi there everyone, welcome back to the channel. I'm the GCSE science teacher. In today's video, we're going to be revising all the key content for GCSE chemistry students, particularly looking at paper 2 content. And this is going to encompass all of the triple science topics for that paper. So if you haven't already seen my previous video on paper 2 topics for chemistry, I will link that for you in the description box. But I would recommend you watch that one as well, because that has a lot of the key content that you need for that exam. This video is simply the triple science additional topics that you need to revise. So I hope you find this video helpful. If you do enjoy it, let me know by giving it a thumbs up, share it with someone else so they don't miss out. And thank you so much to everyone who has subscribed, left a lovely comment, shared these videos, just all of it. Thank you so much. It's really amazing to have such an amazing community here. So thank you so much. And if you would like to join us, you want to be part of this community, just click subscribe. It's absolutely free. Click the bell so you get notified, and let's get started. So the first thing we're going to talk about is this organic chemistry topic. And although you need to know about hydrocarbons specifically for triple content, you need to know about cracking of alkenes. So as a bit of a recap, remember that alkenes are part of a homologous series. They are examples of hydrocarbons, so they only contain hydrogen and carbon. But the difference between those and alkanes is that an alkene is essentially an unsaturated hydrocarbon because it has a carbon-carbon double bond. Remember, carbon can only form 4 covalent bonds. So in this case, because there's 2 carbon atoms you can see here, they're covalently bonded to form those double bonds, a very strong bond. It now can only form several bonds with other hydrogen atoms. So each of those carbons you can see will only be able to combine essentially with 2 hydrogens. So that's slightly less than what you'd see in an alkane. So that being said, if we were to write a general formula for alkenes, we would have something that looked like this. So we'd have CnH2n. So for the amount of carbons you have, you're going to have double the amount of hydrogens. This is different to, say, alkanes, which had a general formula of CnH2n plus 2. Those were classified as saturated hydrocarbons, just as a bit of a comparative point. Something else to mention: because you need the carbon-carbon double bond, there's no such thing as methane. There's methane, that is just 1 carbon atom covalently bonded to hydrogen atoms as well, but that's an alkane, there's only 1 carbon there. But in the case of alkenes, you need at least 2 carbon atoms to form that double bond, so therefore methane doesn't exist. We only have ethene, propene, and butene. There are many, many more, of course, as the chain length increases, but those are the key common ones that you should know for GCSE. Ethene just means there's 2 carbon atoms, propene is 3, and butene is 4. Now, how do we actually test for alkenes? Well, we can use something called bromine water. And in the beginning state, bromine water is a liquid which is see-through, it's transparent, and it has a brown, reddish, orangey colour. Now, in the presence of alkenes, it actually decolorizes. So it doesn't go clear, it's still clear throughout the whole process. Decolorizes, it just means the colour of it is no more. It doesn't have a colour to it. That's a really key term to use. Never say it's just clear, because it was clear to begin with. It just loses that colour if there are alkenes present. Now, alkenes we find in the case of crude oil. Remember, they are hydrocarbons. We can extract that from the Earth's crust, but in their natural state, they're not particularly useful, especially if the carbon chain length is very, very long. So we actually can break down alkenes to make them more useful and put them into 2 processes. Essentially, this is called cracking of alkenes, and this is a process you need to be aware of. Just like fractional distillation was a process you need to know for, say, alkanes, alkenes can be broken down into better, more usable fractions. So the first thing you want to know is there are 2 types of cracking. We have steam cracking and we also have catalytic cracking, which kind of describes what each of them do, but you need to know their conditions. So in the case of steam cracking, you need to have very, very high temperatures, specifically over 800 degrees Celsius, so incredibly high. And of course, with this comes a lot of financial cost. There's another version of this called catalytic cracking, and catalysts, as we know, are essentially substances that don't get used up in a reaction. They lower the activation energy, and they essentially help the reaction happen by reducing the amount of energy needed for that reaction to occur. So it can be quite a beneficial thing to do. It doesn't get used up. It provides an alternative route. So catalysts are really great. Essentially, what you need to know for catalytic cracking, the catalyst is called zeolite, and this is essentially made of aluminium oxide, silicon oxide. It's just a substance that helps lower that activation energy. You also need to know that the temperature is slightly less. So it's around 550 degrees Celsius. So that's because that catalyst has provided a lowered activation energy. So this can be a really good way, financial incentive that people use in industry. So catalytic cracking is another option to break down those alkenes. Now, you might be thinking, what can these alkenes be used for after the process of steam or catalytic cracking? In the case of this, we want to know that they can be used for things like fuel. So just to finish off the alkenes topic, we need to know a few reactions that occur with alkenes and different substances to form new products. And in each case, there may not be a hydrocarbon that forms. It may be something slightly different. So in the first case, there is a hydrocarbon that forms. So if alkenes react with hydrogen, we call this a hydrogenation reaction. It will form an alkane. And the reason for this is because the double bond that's formed in the alkene, let's say, for example, propene, where there's 3 carbon atoms and there's a double bond within that structure, this will form a single bond with other hydrogen atoms to form propane. So the carbon chain length doesn't change. It's just the fact that the functional group of the alkene now has broken apart and reorganized itself in a chemical reaction. And that's why we get essentially a saturated hydrocarbon at the end of that alkane that forms. So there's no longer any double bonds present. The next reaction you should know is alkenes when they react with water, specifically steam, and this will form an alcohol. Now remember, an alcohol is not a hydrocarbon, because if the water molecule, if we look at it, is H2O, there is an oxygen atom here. And conservation of mass laws tell us that if we have some atoms at the beginning of a reaction, we will need to have the same atoms at the end of a reaction. They just are rearranged in a chemical formula slightly different to how it was in the beginning. So essentially, if we have an alkene and steam or water, this will form an alcohol with a functional group of OH, and we'll talk about alcohols in a bit more detail later on. The last reaction is when an alkene reacts with halogens. Now remember, halogens from paper 1 we learned are found in group 7. So these are all non-metals. These therefore are negatively charged ions. It's worth just remembering those bits of information. So what happens is when an alkene and halogen react together, they form something called a halogen alkane or haloalkane. Either way, it's fine for you to use that term. And essentially the functional group is that halogen. So it could be chlorine, fluorine, iodine, bromine, any of those you see in that structure, you'll know is that particular substance, and that's the functional group. So yes, that's just a bit of detail on that. And now we're going to talk about alcohols. So we obviously know that alcohols are formed when alkenes react with steam, but we also need to know a little bit more detail about that. So for example, this is a homologous series, just like alkenes are, just like alkanes are. Alcohols are their own little homologous series because they all have similar properties, similar functional groups, and that kind of thing. So you need to know that they all can have the same suffix. So they all end in ol, so methanol, ethanol, propanol, butanol, and the functional group is OH. Now, if we were to burn alcohols, we can say this is a combustion reaction. A lot of them are highly flammable. So alcohols can actually be oxidized without combustion to produce something called a carboxylic acid. So they can be useful in combustion reactions, but they can also be oxidized without combustion or to burn something to produce a new group called carboxylic acid, which is something you should also know as well. You also should be aware of a biology topic at this stage, and this is something called fermentation. Now, you learned about it in biology, and it's a cross-curricular link that they like to share in chemistry as well. So just as a recap, remember that ethanol, one of those alcohols, can be formed from the anaerobic respiration of yeast when glucose is broken down without the presence of oxygen. And ethanol is found in a lot of alcoholic drinks. If there was some oxygen present, this can actually cause ethanoic acid, otherwise known as vinegar. So if there is a problem with the reaction, this is why a lot of wine and beer can often taste vinegary if anyone was to consume it. So ethanoic acid, otherwise known as vinegar, is an example of when an alcohol reacts with an oxidizing agent, aka something with oxygen in it. And that ethanoic acid is the carboxylic acid. You also form water as well, but the bit they're interested in you knowing is that when an alcohol reacts with an oxygen atom or an oxidizing agent, something with oxygen in it, it will form that carboxylic acid. And you should know the functional group of a carboxylic acid, which is COOH. So instead of the alcohol functional group OH, you now have a carbon and an oxygen, and there is a double bond there, and that's really important for you to know. Also, the suffix of carboxylic acids being oic acid, that's a real key indicator. And yes, if you're thinking, is this an acid in the true sense? Is it lower than pH 7? The answer is yes. It will be kind of a reddish orangey yellow color if using universal indicators. So that's a good way to test for it as well. Now you might be thinking, okay, what if we had to name some carboxylic acids? How would I know if there was, like, say for example, ethanol reacting with an oxidizing agent? You can see it forms ethanoic acid. The kind of same rules apply. So if you have, say, methanol, it would form methanoic acid, propanol, propanoic acid, butanol, butanoic acid. They kind of shows a similar theme here. So carboxylic acids follow that kind of same idea. So meth, eth, prop, and bute essentially stand for 1, 2, 3, and 4 carbons, that is. So it's a good way to remember it. Something else to mention, carboxylic acids can actually react with alcohols to make esters. So everything's essentially reacting with everything else. I would highly recommend you make flashcards on this so you kind of understand the steps. But yeah, carboxylic acids react with alcohols to form esters. Now, esters are what we find in things that smell really nice, like perfumes, and they're really useful in cosmetic products and things like this. So if you're looking for an ester, it has a functional group of COO instead of COOH. Just be aware of that difference between carboxylic acids and esters. Now, they don't want you to know a huge amount of ester information, if you will. They just want you to know simply the reaction between ethanol and ethanoic acid, so the alcohol and the carboxylic acid, and this will form ethyl ethanoate and water. That's kind of the key one they want you to be aware of. They're not necessarily going to ask you about any of the others, but it's worth just being aware of that specific example. Now, last but not least, you need to know about polymers and monomers. And you should know that there are lots of biological polymers we've talked about before, things like DNA, proteins, starch, cellulose. There are loads of other examples, but these are some common ones. Essentially, a polymer is a repeating unit of individual subunits called monomers. Like a beaded necklace, each bead is the monomer, the whole necklace is the polymer. And as you can see here, if we had the polymer, we can show just a section of it with those square brackets, and the double bond has essentially been flipped out, so it folds over the top of that double bond, that sort of square bracket, whereas the monomer itself, you're showing those double bonds and you're showing the single unit. So there's normally an N number next to the square bracket next to the polymer, and that just indicates how many repeated units there are. So if there's a N number of 10, there'll be 10 lots of that monomer essentially bonded together. So that's kind of the simplified version of this. So chemical analysis is the next topic, and although there are some crossovers here with the combined higher and foundation topics, you do need to know a little bit extra. So we're going to go over this for triple scientists. So positive ion tests, negative ion tests. Let's just first of all clarify, how do we know if something is a positive ion or a negative ion? Remember, another way of saying positive ion is a cation, and a negative ion is an anion. But how do you know the difference? So if you're looking in the periodic table, anything on the left-hand side, this is what we classify as a metal. Now, metals will always form positive ions because they are able to donate their electrons. So they will form a positively charged ion. Sometimes it's just +1, just a positive charge, just one positive charge because they've lost one electron. Sometimes it can be +2, +3, depending on how many electrons are lost. Now, in the case of this situation, there is only 2 metals that you should know in this case that have a +2 charge, so calcium and copper. The others, lithium, sodium, potassium, they have a plus charge, just one electron has been lost, okay? Negative ions, therefore, are anything that are non-metals on the right-hand side of the periodic table. So we're thinking about things like the halogens, so group 7 elements that have a minus charge, a -1 charge, okay? So chlorine, fluorine, bromine, iodine, all of those are negative ions. So that hopefully has clarified a couple of things. And the reason they're negative, just to make this crystal clear, is because they essentially accept electrons from metals, and that's how you get ionic bonding, right? So anyway, let's talk about this. Positive ion test. How do we test and know what ion is which? Well, we would need to burn these, and we'd basically essentially see that lithium will form a crimson flame, which is like a really nice red color. Sodium will form a yellow flame, and potassium will form this lilac colored flame. Copper is a green flame, and calcium 2+ is an orange-red flame. So like I said, worth making flashcards on these so you have those key ideas in your mind. The next one is the negative ion tests. So if we look at silver chloride, we'll see that it has a white coloured precipitate. If we were to look at silver bromide, we'll see it has a cream coloured precipitate. And silver iodide is a yellowy formed precipitate. Now you might be thinking, how is this actually done? So we know the results, we know that they're positive results for each of those halide ions. There are other negative ion tests, and I'll talk about those in a moment, but these are the halide ion negative tests, or negatively charged ion tests for halide ions. So how do we do this? So essentially, you're going to need to use a few drops of dilute nitric acid, and you're also going to want to use a few drops of silver nitrate solution. Now, the acid is really important in this case because we want to use nitric acid. If we were to use something like hydrochloric acid, this wouldn't be a good idea because hydrochloric acid has chlorine or chloride ions inside. And because chlorine or chloride ions, they're part of the halogens, that essentially would give a negative or a false positive result because essentially chlorine, because it's in group 7, just like bromine, iodine, fluorine, all the other halogens, if we have lots of chlorine ions in that solution, it's going to give us a false result. So that's why nitric acid is used, and that's something they could ask you to explain. So there are 2 other negative ions that you should be aware of. And unlike things like lithium or calcium, where it's just one element, I know they're positively charged ions, but in the case of these 2, they're negatively charged ions, but they have quite a larger structure, if you know what I mean. So I'll put them on there. We've got carbonate ions, and we've also got sulfate ions. They are negatively charged overall, but again, some students get a bit confused with these, so it's worth just making a flashcard on them. But let's talk about them. So the first one is carbonate ions, so CO3 2-. And essentially they're detected by using dilute acid. And what will form is this kind of, gas bubbles will form. And this is carbon dioxide that forms. And we can actually test for this by using lime water. And that should go cloudy if carbon dioxide is present. This kind of cloudy milky solution will be used to determine that. The other negative ion is sulfate ions, like I said, so SO4 2-. And essentially, when we use a few drops of dilute hydrochloric acid and a few drops of barium chloride solution, a white precipitate will form if those sulfate ions are present. So those are a couple of other things to mention. And lastly, we have gas tests and then metal hydroxide. So a couple of gases that you should be aware of include hydrogen gas. You'd want to use a lit splint. You'll find that if the hydrogen is present, there will be a squeaky pop sound. If there's oxygen gas, we will use a splint that is kind of like lit, but not really. So we would call this a burning splint. And if there is oxygen present, it will relight that that splint as well. Carbon dioxide, kind of mentioned this already, but lime water will turn cloudy in the presence of carbon dioxide. And if chlorine gas is present, it's very toxic. So hopefully a fume cupboard is being used, but it will bleach litmus paper white. Now let's talk about metal hydroxide. So we have a couple of different ones. We've got iron. We've got iron 2 oxide that has like a greenish colour to it. We've got iron 2 ions, which have like a reddish colour to it. Copper 2 ions, and then which has like a bluish colour to it. And we then also have aluminium, calcium, magnesium ions, which have a white colour to it. And again, just to help you out, we often use hydroxides to essentially find the colour of these precipitates. So sodium hydroxide is a good one to use. I also would recommend you understand the word precipitate. That's just a insoluble substance. So something like a solid that doesn't dissolve. So that's why when I'm talking about precipitates, you often find them in solutions. They're just little bits of powdery substances that haven't fully dissolved. And that's why we can see the coloured compounds, but that's why you can also sometimes see the colour changes as well. So it's worth just being aware of that keyword for this topic. So here is the using resources topic. We're going to be talking about the different materials that triple scientists need to know, and also the Haber process. So let's talk about the first material. It's an alloy. Now, an alloy is a mixture of metals. Specifically, we're thinking about ferrous metals, so steel, which contains some iron. And that also, by the way, because it contains some iron, it is a magnetic material. But it's an alloy because it's not a pure substance, it's actually a mixture. And people use alloys because we can actually strengthen metals, we can give them different properties, we can actually mix them together. So if we have a finite resource, something like iron or copper, we can actually almost dilute it down a little bit. So we still get some of the benefits of that particular metal, but we can actually mix it with other things to either amplify or cut costs. The next one is polymers. Now, we've talked about biological polymers, of course, but polymers in the case of materials, we're talking specifically about plastics. And there's two different types of polymers or plastics that you should know. So there's one called thermosetting, and these are polymers that don't melt very easily. And that could be in the case of things like plug sockets or medical device technologies. And that's because at high temperatures, if they were being sterilized or there's electricity going through them, we don't want them to melt. So they have longevity. This, however, means they're not easily recyclable. So there is a bit of a downside, but hopefully with their longevity, we won't need to recycle them. The other one is called thermosoftening polymers. And these are ones that really melt quite quickly and can be easily recycled. So you're thinking about things like plastic bags or other products that could easily be recycled, like plastic bottles that can be reformed and reshaped. And they're kind of single use, multiple use, but they don't have a particularly long lifespan. Another type of material you should know is something called a composite material. And this is used to strengthen specific materials. So some good examples of composites include soda lime glass, which essentially is a mixture of sand, sodium carbonate, and limestone. This is used in making buildings, making products that can be used in industry. We also have something called borosilicate glass, which is also made of sand, but also something called boron trioxide. Another common composite is MDF wood, which is found in lots of general household items like desks and chairs and cupboard doors and tables. Essentially, MDF wood is made of sawdust, wood chips, and resin, so it's much cheaper than using solid oak wood from a tree. This also helps with environmental factors like deforestation, so it's a good option. And also concrete. So concrete we know is used for buildings, roads, that kind of thing. This is made of cement, sand, and gravel, so it's a mixture of things. And this is to help with strengthening the product in a more cost-effective way and potentially with environmental factors considered as well. So with the Haber process, the reason we have the Haber process in the first place is to make ammonia, and ammonia is used for fertilizers. So you need to know the reaction of nitrogen, which is a gas, and hydrogen, which is a gas. They react together to form ammonia, also a gas. This is a reversible reaction, however, so we can have the opposite occur as well. So ammonia can be broken down into nitrogen and hydrogen. However, we want to make sure that the product that forms in abundance is ammonia. So different conditions need to be maintained to ensure that happens, and it favors that forward reaction. So the first thing you need to know is the catalyst for the Haber process is iron. Remember, a catalyst reduces the activation energy, increases that collision frequency because that activation energy is lowered. We can also increase the temperature as well. So 450 degrees Celsius essentially causes more collisions to occur between those particles of nitrogen and hydrogen, and therefore more ammonia is formed. There is also a higher pressure. And the reason for this is because at high pressure, 200 atmospheric pressure, this simply forces those particles together. So there's a higher collision frequency, so more ammonia is made. But because it's a reversible reaction, we want to make sure that the forward reaction is favored. And this goes back to this idea of Le Chatelier's principle. So he basically came up with this idea that if a change occurs in a reversible reaction, the opposite will happen to counteract that change. So essentially, you need to know that because there's a catalyst, it will actually increase the speed or the rate of reaction in both directions. So the pressure condition is really important. Essentially, the reactant side of the equation has more molecules of gas or higher moles of gas. And this means that if the pressure is increased, the equilibrium will actually shift towards the production of ammonia. And that's a really important concept for you to understand. And I would recommend watching part 1 of this topic so you actually can see that being explained a bit more. And I'll link that for you at the end of this video and in the description box. And that's it from me today. I've been the GCSE science teacher and you have been curious. If you enjoyed this video, let me know by giving it a thumbs up, share it with someone else, and do subscribe to join our amazing community here. Thank you so much for all of your support. I hope your exams are going well. Let me know in the comment section what you're revising at the moment. If you have any questions about science GCSEs, maybe you're in year 10 and you're doing your mock exams, let me know if you have any questions or if you would like to request specific topics. If you want more revision from me, check out my other videos. I'll leave a playlist for you. I also have an Instagram and TikTok where I share lots of revision as well. Everything is at the GCSE science teacher. Thank you so much for your time. Have a great day and I'll catch you in the next one.